Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we will demonstrate data preprocessing techniques on real-world datasets. Data preprocessing involves several transformations that are applied to the raw data to make it more amenable for learning. It is carried out before using it for model training and predictions. Earlier, we saw many data preprocessing techniques. These techniques are used for data cleaning, feature transformation, feature selection, and feature extraction. In data cleaning, we typically perform data imputation in order to fill up the missing values. Then we perform feature scaling in order to bring all features on the same scale. Polynomial features are useful in order to get higher order degree representation of the dataset. Discretization is used to divide the continuous attribute into different bins. Then we also need spatial handling of the categorical features. Generally, there are diverse set of features in the dataset and we need to apply different transformations on those features. So we have composite transformers for that. Then usually not all features are important for machine learning training, and feature selection methods help us to select useful features for training. That leads to more efficient machine learning algorithms. Then finally there is feature extraction, where we are trying to form new set of features with existing features. These transformations have to be applied in a specific order, and the order can be specified via pipeline. We need to apply different transformations based on feature types. Feature union helps us to perform that task and combine output from multiple transformations into a single transform feature matrix. In the end, we'll visualize these pipelines in order to understand whether we have set it up correctly. Let's begin by importing basic libraries. So to begin with, we are importing basic Python libraries. However, it is a good practice to have all import in one cell arranged in an alphabetical order. This helps us to weed out any duplicate imports and some such kind of issues. However, here, since we are demonstrating different techniques, our imports are scattered all over this particular collab. Let's start with feature extraction, and the first method or first utility is DictionaryVectorizer. So many times the data is present as a list of dictionary objects, something like this. So here we have data with 4 samples, and each sample has 2 features, age and height. The data is currently present as a list of dictionary objects. But machine learning algorithms expect data in matrix form of shape n cross m, where n is the number of samples and m is the number of features. So DictionaryVectorizer converts a list of dictionary object to feature matrix. So let's see how to do it. So we first import DictionaryVectorizer class from sklearn.feature_extraction module. We instantiate DictionaryVectorizer object with sparse equal to false. Then we call fit_transform. Now remember, this is a transformer, and transformers have this method fit_transform. So the fit learns the relevant parameter for the transformation, and transform actually carries out the transformation of the original data into new data. So now we have DictionaryVectorizer and we call fit transform on that. So now you can see that this particular list of dictionary objects, they have been converted into a matrix form with shape 4, 2. So there are 4 samples and each sample has got 2 features. So you can see that age is copied in the first column and height is copied in the second column. Let's talk about the next utility, which is data imputation. So many machine learning algorithms need full matrix, full feature matrix, and they may not work in presence of missing values. So data imputation identifies missing values in each feature of the dataset and replaces them with an appropriate value based on a fixed strategy. So the missing values can be replaced by mean, median, or mode of that feature, or some user specified constant value. So we have SimpleImputer utility in sklearn library. So we import SimpleImputer from sklearn.impute module. So the missing values could be of any type. They could be integer, float, string, np.nan, or none. The default missing value for SimpleImputer is np.nan. If we have np.nan present in any of the sample, then we consider it as having a missing value for that particular feature. Now we also need to specify what kind of strategy we should be following in order to fill up those missing values. We can either use mean of the feature for which the value is missing, or median of that feature, or most frequent value of that feature, and then constant. Constant is something that user has specified in fill_value argument. Now most frequent and median are different. Most frequent make sure that the value that is filled is one of the values that are present in the in that feature column, whereas median will give us the median along each column. Now add_indicator is another parameter. It's a Boolean parameter, and when that is set to true, it returns missing value indicators in indicator_member variable. Now we use mean and median as strategies for numerical data, whereas most frequent and constant strategies are used for string or numerical data. This should actually be median and not mode. We'll make that change in Colab. Now let us perform data imputation on real-world dataset. Here we'll be using heart disease dataset from UCI machine learning repository. It has got, so we are going to read this data from CSV. So this is how, if we know the location of the CSV file, we can call pandas.readCSV, read_CSV function, and read the CSV file into a data frame. So this heart disease dataset has got 14 columns in it, out of which the last column, which is number, which is diagnosis of heart disease, is a label, and there are 13 different features for this. There is age, sex, chest pain type, then resting blood pressure, serum cholesterol, fasting blood sugar, resting electrocardiographic results. Then there is maximum heart rate achieved, exercise induced angina, then depression induced exercise relative to rest, then slope of the peak exercise ST segment, number of major vessels, then there is TAL. So there are such kind of 13 features. If you are interested in learning more about this dataset, we have provided a link over here. You can click on this link and get more information about this dataset. Now first we will check whether there are any missing values in the dataset. So missing values can be checked via dataset description or by checking number of nans or np.nan or np.null in the data frame. So such a check is only possible for numerical values. For non-numerical features, we can list the unique values and check if there are values like question mark, which are typically missing values in non-numerical features. So we first call the info method on the data frame, and you can see that there are 303 entries, and there are 13 different columns. There are 14 different columns. It starts at 0, so there are total columns are 14, and we also have the data type for each of the column. The columns CA and THAL are non-numerical columns. So we'll first check whether there are any missing values in the numerical columns. So for that, what we do is we call is null and then sum it across all the rows, and you can see that for the numerical feature there are no missing values because this has come out to be 0. Now for non-numerical features, let us list the unique values. We can list them by calling unique on the column. So you can see that in CA we have this value is a problematic value, there is a question mark here, as well as in THAL there is a question mark, and both of these question marks means that there are missing values. We can count these missing values. So in CA there are 4 missing values, and in THAL there are 2 missing values. Now what we'll do is first we'll replace this question mark with none, and then we will use the SimpleImputer with mean strategy. So there are 2 variations that we'll try. We'll try first with add indicator equal to false, which is a default choice. Now you can see that here we have instantiated SimpleImputer object. We call fit, and then we call transform. Alternatively, we can also call fit underscore transform, and you can see that the dataset of the transform feature matrix, the shape of that is 303, 14. So add indicator equal to false only imputes the missing values. It doesn't add any columns to it. So there were 14 columns in the input, and we now also have 14 columns in the transform feature matrix or in the output. Now if we pass add underscore indicator equal to true to SimpleImputer, as you can see over here, and then we perform the same steps where we first fit and then transform, and now if you print the shape of the output feature matrix, now there are 16 columns here. There are 2 more columns that are added here. So what are these 2 columns? So we had 2 columns with missing values. So when we set add indicator equal to true, we add an additional column for each column containing a missing value. So since we have 2 columns containing the missing values, we added 2 more columns, and those columns are basically, they contain Boolean values. So if a value is true, then we know that that value was missing in the original feature matrix, and that value has been filled up through the imputing with, in this case, with mean strategy. So that is a Boolean kind of a column, has got true and false values. So it is useful. Some machine learning algorithms can take care of of such kind of filled missing values if they wish. So the next utility is feature scaling. So feature scaling transforms feature values such that all features are on the same scale. It is useful for faster convergence. So typically the iterative optimization algorithms like gradient descent and its variants, they're pretty sensitive to the feature scaling. If all features are not on the same scale, gradient descent might take longer to converge. And in case of some of the machine learning algorithms like SVM, KNN, K-means, we compute Euclidean distance among input samples. So if the features are not scaled, this computation also gets impacted. Now note that if you are using tree-based machine learning algorithms, they are not affected by feature scaling. So in other words, feature scaling is not really required for tree-based machine learning algorithms. So feature scaling can be performed with the following methods: standardization, normalization, or max absolute scalar. We'll demonstrate feature scaling on abalone dataset. Abalone is an edible snail, and there is a data collected about this snail in order to estimate their age based on other physical characteristics. So again, we are going to read this data from CSV. We are providing the part to the CSV file. It comes from the UCI machine learning repository. There are 8 features, which is sex, length, diameter, height, whole weight, shucked weight, viscera weight, and shell weight. And based on these physical characteristics, we have to predict ring, which is a target variable, and ring denotes age in terms of years. So if you are interested in knowing more about this dataset, follow the link which is given over here. As a first step, we'll examine the dataset. So feature scaling is performed only on numerical attribute. So we'll first check which attributes are numerical attributes in this dataset. We can see that except sex, all other attributes including the output or the target are numeric. So optionally, we can convert non-numerical attribute to numerical attributes. So for example, here we have 3 unique values for sex, M, F, and I, and we can convert them to numbers by assigning one number to each of the unique value over here. So we will denote M with value 1, F with value 2, and I with value 3. Now if we again call info on this after replacing these strings with numbers, we can see that now we have all numerical attributes including sex. We do not want to perform feature scaling on the label, hence we first separate labels from the features. Now the label is separated. There are only 8 columns in this particular data frame containing the abalone data. We'll first examine feature scales. So there are 2 ways to do this. One is with statistical methods and second is through visualization. We'll look at both the methods. You may wish to use one of them in the real world data set or in the real world setting. So first we use the describe method on the data frame, and we have transformed it for better visualization or better representation in the tabular form. So you can see that there are 4177 examples or rows in this dataset, and the mean and standard deviation are quite different from one another. You can again confirm this with a variety of visualization techniques and plots. You can also see the minimum value and the maximum value, they are also different. So that actually tells us that these features are indeed on different scales. So we can use bunch of visualization tools like histogram plot, kernel density plot, box plot, or violin plot. Let's look at these plots one by one. We can plot separate histograms, or we can plot a combined with histogram. So here you can see separate histogram, one for every feature. Let us combine these different histograms into a single histogram, and you can see that different features have different ranges if you observe histograms for different features. For example, this particular feature, which is probably whole weight, that weight is kind of has larger range compared to, let's say, height. Height has smaller range than weight, and you can observe these kind of details from this histogram and conclude that different features are indeed on different scale. We can confirm the same thing with KDE plot. KDE plot is a kernel density plot that uses Gaussian kernel in order to generate these feature distributions. So you can see that different features have different distribution. The height is peaked around a value very close to 0. Then this is length, which is peaked around value between 0 and 1, and so on. So you can see that different features are on different scales. We can use box plot for confirming the same. And box plot, if you are not aware, it has got it has got it has got four different things. So for example here, right, so this box that you see here, this is 25th quartile, this is the median, the middle line over here, this 75th quartile, and the extremes are, this is a minimum value and the maximum value. And you can see that here, since there are only three values in 6, the minimum value coincides with the 25th quartile, then there is a median value which is 2, and then the max value and 75th quartile, they coincide. So you can see that these are different distributions. This is a way of demonstrating the variability in features. You can see that whole weight has got a larger range. The minimum value is 0 and max value is somewhere close to 3. And some of these points that you see here, these are kind of outlier points. They are denoted by they are outside these they're outside these lines. These are mostly outlier points, and there can be outliers on both the sides. So we can visualize the same information with violin plot. So only difference between box plot and violin plot is that violin plot uses kernel density estimation and then plots that very much similar to what box plot does. But here, instead of getting just box, we also get the density information for each feature. So all that we can conclude by looking at these plots is that features are indeed on the different scales. Now we will perform scaling first with normalization. In normalization, what we want to do is we want to normalize features such that the resulting features are in the range between 0 to 1 or between -1 to 1. We use max absolute scalar to transform features in the range -1 to 1 and min max scalar to transform features in the range 0 to 1. So max absolute scalar is present in sklearn preprocessing. And we call fit underscore transform on the input features. So the original features are basically 4, 2, 5, -2, and -100. We reshape it to some. So this is a vector, right? So we reshape it to become a matrix, and then we call fit transform on this particular matrix, and you can see that now the transform representation is in the range -1 to +1. So we have minus 1 value for the largest number, which is largest negative number here. So largest number happens to be a negative number, so we get a value of minus 1 over here, and the other values are scaled as per this formula. So where the scaled value is equal to the value divided by the max absolute value, and the max absolute value is calculated as max of the maximum value and mode of the minimum value. So based on that, the maximum absolute value is calculated. Second option is to use min max scalar, and in min max scalar we again instantiate object of a min max scalar, which is imported from sklearn.preprocessing module. We call fit underscore transform, and we get the transform features with min max scalar, and here the range will be between 0 to 1, and the formula is the old value minus the minimum value divided by the range, which is max minus mean. Now what we can do is we can look at mean and standard deviation of the transform feature matrix, and you can see that most of their means are now kind of comparable, and the standard deviation is also not that high. So we can again compare this by through visual method by plotting the histogram. We can see that most of the features are in the range between 0 to 1. And we can also see that the box plot, all the values are pretty much in the range between 0 to 1. It has not changed the distribution per se. The outliers have remained as outliers, but the entire range is scaled such that it is in the range between 0 to 1. Same thing you can see with Boolean plot or KDE plot. The shape of the distributions remain the same, but the range is now between 0 to 1. The other way of performing feature scaling is through standardization. In standardization, we get the new value by subtracting the mean value of the feature from the old value and dividing this difference by the standard deviation. We use standard scalar utility from sklearn.preprocessing module, and we call fit underscore transform on the original feature matrix, and we get a standardized feature matrix. Now you can see that the standard deviation for each of the feature is 1, and we can again find this out. Here the range of the features can be different, but all of them have mean of 0 and standard deviation of 1, and you can see that all of them are picking around the value 0. So you can see also in the box plot that all of their mean value or the median over here is aligned, right? They are all aligned to 0. So see the difference the way we are doing standard scaling and the other and the normalization. You can see that in scaling they are kind of aligned on the mean value, whereas in the earlier method they were aligned on the range.